Developing an engine that generates electricity from various heat sources and that anyone can replicate using simple means has been my goal for many years. The next step is to use the elegant thermoacoustic engine to drive an electric generator. In the last video, I used the finite element method to design a linear generator theoretically and started building it. Now I will show you the entire manufacturing process of the generator and present the first performance and efficiency tests. My main aim is to develop a simple, reliable and powerful engine, for example for a combined heat and power plant, which anyone can build themselves without the need for expensive machinery. The basis is a thermoacoustic engine, which now has enough power to drive a generator. This is important for the upcoming extensive development steps in order to be able to directly measure which changes bring about an increase in performance. After several attempts with a turbine, oscillating stepper motors, a push crank mechanism, and a simple radial linear generator, I would now like to test a more powerful, flat linear generator. In the last video, I demonstrated its design using the finite element method and the FEMM program. Now it's time for the finishing work, and here I would like to show you the entire manufacturing process from start to finish as requested by many in the comments. The flat linear generator consists of an iron housing with 5 pairs of magnets facing each other. The copper coils oscillate through the strong magnetic field between the magnet pairs, inducing a current in the coils. In the initial designs, I wanted to use linear guide rails, but the magnets exert such a strong force on the guide carriages that I now use simple round guide rails. First, I milled and drilled the iron cage and cut the threads for assembly. Gluing the magnets precisely onto the iron plates was only possible with the help of 2 printed templates, and even then it was still difficult to overcome the strong magnetic forces. I designed the carriage for the coils and the mounts for the round guides in FreeCAD and printed them from simple PETG. The core of the coils is also made from PETG. A core made of iron discs would be ideal here, but the magnetic forces inside the iron cage are so strong that the engine's power is not yet strong enough for this. I wind and glue the coils in a PTFE mounting from which they can be easily removed once the resin has dried. For comparison tests, I tried one coil made of 0.5 mm coated copper wire with about 50 turns and one coil made of 0.2 mm copper wire with about 200 turns. The construction of the coils is, of course, very important. I still lack both of precise technical knowledge and the experience. The coil made of 0.5 mm wire has a low resistance of 0.2 ohms, but the 50 turns are probably very few. The 0.2 mm copper coil has a very high resistance of about 10 ohms, but the 200 windings are most likely better suited to generate usable voltages. I would be very grateful for your help in the comments, especially regarding the design of the coils. I need to see if I can simulate this with FEMM or calculate it in another way. So far, I'm just trying a few things out. Now the coils can be inserted into the carriage and fixed in place. The connection of the coils to the outside is impractical, which I still have to solve with sliding contacts made of carbon brushes or similar. However, moving coils offer several advantages over moving magnets that I do not want to forego simply for the sake of simplified cable routing. Moving coils are lighter than moving magnets, and I want to keep the moving mass low at almost any cost. Even the use of a tiny grub screw made of only very low magnetic stainless steel created a clearly noticeable resistance between the magnet pairs. In my present design, I do not use any moving magnetic components in order to achieve rapid oscillation despite the currently still low power levels. This enables the generated power to be adapted very precisely to the thermoacoustic engine's power output, which will change a lot during development. The construction of the iron cores is much simpler. Only the iron core and the coils, which may be used at a later stage, must consist of individual discs of iron that are insulated from each other in order to avoid eddy current losses. Another disadvantage is that the linear generator in its current form cannot be used to start the engine. As the magnets are arranged in pairs with opposite poles, I don't see how an induced magnetic field in the coils could generate a force on the carriage to start the engine. Assembly and alignment are simple, and initial tests with slow movement show a nice alternating current curve on the oscilloscope. As expected, the 200 turns of 0.2 mm wire generate a higher voltage than the 50 turns of 0.5 mm copper wire. The simple test rig generates a lot of friction due to the simple crank mechanism and only allows slow speeds. Therefore, the voltages generated are very low, and rectification for effective power measurement is difficult. The voltage drop across normal diode rectifiers is simply too high. The active diodes I use also have high losses at these low voltages and operate at the absolute lower limit. With a coil made from 0.2 mm copper wire and 200 windings, I was able to measure an efficiency of 2% overall, from the input energy in the drive motor to the measured output power of the linear generator. Here, one must take into account the many influences, but for a first result with these simple means, I don't think it's as bad as it sounds. I will now use the experience I have gained to improve the carriage, optimize the coils, and then attach the linear generator to the thermoacoustic motor. I hope to achieve higher movement speeds and better results in order to obtain a reliable performance measure for the thermoacoustic engine. As always, I look forward to your comments, especially regarding the optimization of the coils, but also to general suggestions and opinions on how the linear generator can be improved. I would like to express my special thanks to my supporters on Patreon and all channel members. Thank you very much for your interest.